Hello everyone, I am Anshu Khanna and I teach at Sri Chaitanya Vijayawada Goshala. Today we are doing the chapter of collision. This is a small chapter, not too much of concept, easy chapter, scoring chapter. And as you know, one question comes from this chapter every year. So let's start doing it without wasting time. So let's talk about collision. Let's say there are two bodies in space. The first body moves with speed u, second body moves with speed v in the same direction. For these bodies to collide, the one behind and moving with speed v must have a higher velocity than the one in front. Then only they will approach each other and then they collide. Now here in collision you need to understand the whole process. First the bodies come into contact. After coming into contact the bodies deform and the bodies keep on deforming till the time they attain a common velocity. So first the bodies come into contact, then they start deforming, then there is an instant of maximum deformation. Remember that at the instant of maximum deformation, both of them move with a common velocity, which I have written as v common. Sir, how to find this common velocity? Let's say the first body has got mass m1, the second body has got mass m2. To find this common velocity, you can simply do momentum conservation. You can write m1v plus m2u equals to m1 plus m2 into v common. Understand that momentum is a vector quantity. So if both the bodies are moving in opposite direction, you have to take care of the direction of motion. Now, first the bodies move towards each other, they come into contact, then they keep on deforming till the time of maximum deformation. Once they have attained the maximum deformation, at that instant their velocity is same. They have a common velocity along the line of impact. Then they start reforming and then they separate off. So first contact, then deformation. At time of maximum deformation they have common velocity, then they start reforming and then they separate off. If no external force acts on the system, then you can say the momentum before the collision has to be equal to momentum after the collision. Why? Because during the process of collision, the first body applies force on second body, let's say towards right, and the second body applies force on first body, let's say towards left, and they apply force on each other of equal magnitude in opposite direction for equal frame of time. So the momentum transferred by first body to second body is equal and opposite to the momentum transferred by second body to the first body. For doing momentum conservation, we can write m1v plus m2u has to be equal to m1v dash plus m2u dash. Now kids, for this particular type of collision, I can say one thing for sure, that during collision, the first body applied force on second body towards right. So this velocity u dash after the collision must be greater than the velocity before the collision u. You have learned something called coefficient of restitution, and this is taught as coefficient of restitution equals to velocity of separation upon velocity of approach. Velocity of separation is the rate at which the separation increases after the collision. For this particular case of collision, the velocity of this second mass is u dash, the velocity of this first mass is v dash. At what rate the separation between them increases after the collision? Here understand that after collision, this velocity u dash tries to increase the separation, while this velocity v dash tries to decrease the separation. If let's say the first mass is at rest after the collision and only second mass goes away, then you will write the velocity of separation to be u dash. But here the second mass goes away with a speed u dash, while the first mass keeps on tracking it with a speed v dash. So how will you write the velocity of separation? Velocity of separation will be equal to u dash minus v dash. So now why, sir, you took a minus sign? Understand that this velocity v dash is trying to increase the separation, decrease the separation. The velocity v dash is trying to decrease the separation, while velocity u dash is trying to increase the separation. So what will be the velocity of separation? Velocity of separation is the rate at which the separation increases after the collision. So the velocity of separation should be written as u dash minus v dash. What has to be the velocity of approach? Definitely two particles approach each other before the collision. After the collision, they separate. Before the collision, they approach. That's why the collision takes place. How will you write the velocity of approach? See here kids, this velocity of mass m2u is trying to increase the separation, is trying to decrease the separation. This velocity u is trying to increase the separation, while this velocity v is trying to decrease the separation. Which velocity wants the masses to approach? The velocity v wants the masses to approach, while the velocity u wants the masses to separate. So you will write the velocity of approach to be v minus u. One more thing that has to be taken care of. We should take velocity of separation and velocity of approach along the line of impact. What is the meaning of line of impact? Line of impact is the line along which the forces act at the time of collision. To make you understand this, think that there is a gravity-free region. We have a horizontal surface. A mass m comes and strikes, but not vertically down, not horizontally. It strikes at some angle. Now, at the time when the mass is in contact with this floor, in which direction the forces will act? The forces will act along the common normal at the point of contact, and that common normal is, kids, vertical. We say that velocity of separation and velocity of approach are the velocities along the line of impact. Now, when this first mass moves, it has got two velocity, one horizontal velocity v cos theta, one vertical velocity v sin theta. I asked you this question because of which velocity this mass approaches the surface. It is because of v cos theta or is it because of v sin theta? So here you will say that velocity of approach is v sin theta, the velocity because of which it approaches the surface. Now let's say after collision this ball rebounds with some speed u at some angle phi with the horizontal. What should I take the velocity of separation? I can again break down this velocity u into two components, horizontal component u cos phi and the vertical component u sin phi. How to write velocity of separation? Velocity of separation and velocity of approach should be taken along the line of impact, and in this case the line of impact is a vertical line. So you will say the velocity of separation has to be equals to u sin phi. If somebody asks you what is the coefficient of restitution, how to find it? Coefficient of restitution has to be equal to velocity of separation upon velocity of approach, that is u sin phi upon v sin theta. So let's understand this topic more. So now talking about coefficient of restitutions. First, coefficient of restitution is 0 for perfectly inelastic collision. In case of perfectly inelastic collision, since the coefficient of restitution is 0, we can say that velocity of separation upon velocity of approach equals to 0. Velocity of separation upon velocity of approach equals to 0 means that the velocity of separation is 0. When I say that velocity of separation is 0, it do not mean that bodies come to rest. It means that there is no separation along the line of impact after the collision. It means that both the bodies must have the same velocity along the line of impact after the collision, so that the rate of separation after the collision becomes 0. So coefficient of restitution 0 means perfectly inelastic collision, velocity of separation is 0, both the bodies have same velocity along the line of impact. And one more thing, in case of perfectly inelastic collision, the kinetic energy loss is maximum. So if you have got certain amount of kinetic energy before the collision and you have got some kinetic energy after the collision, the loss in kinetic energy of the colliding particles will be maximum in case of inelastic collision, perfectly inelastic collision. Then comes our inelastic collision. Here the coefficient of restitution lies between 0 and 1. Now in these cases there is some partial loss of kinetic energy during the collision, not maximum loss, not zero loss, there is some partial loss of kinetic energy. Then comes our elastic collision. Elastic collision is when the coefficient of restitution is 1. It means that the velocity of separation equals to velocity of approach. The rate at which the particles were approaching each other before the collision, the rate of separation of particles after the collision will be same as that. One more thing, remember that in case of elastic collision, the kinetic energy loss is 0. So kinetic energy before the collision equals to kinetic energy after the collision. This is a famous question asked. In which type of collision you can apply momentum conservation? In which type of collision you can apply momentum conservation? The answer is all of them. You can apply momentum conservation in all type of collision given that there is no external force acting on the system. Second, in which type of collision you can apply kinetic energy conservation before the collision and after the collision? The answer is elastic collision. For elastic collision, you can say that the kinetic energy before the collision equals to kinetic energy of particles after the collision. But listen to the next question carefully. In case of elastic collision, when the coefficient of restitution is 1, can I say that kinetic energy is conserved during the collision? Yes or no? The answer is no. You can't say that. See beta, kinetic energy before the collision is same as kinetic energy after the collision. But during the collision, the body is deformed. So some part of that kinetic energy before the collision gets converted into elastic potential energy in the form of deformation. You know that when you change the shape of spring, some energy gets stored into it. In the same way, initial kinetic energy is there. Some part of it gets converted into potential energy during the deformation. And when they reform completely, that potential energy again gets completely converted into kinetic energy. That's why kinetic energy before the collision is same as the kinetic energy after the collision. But in case of elastic collisions, you can't say that kinetic energy is conserved during the entire collision. As a matter of fact, this is asked, can you do momentum conservation for entire collision in case of elastic collision? Yes, you can. Can you do kinetic energy conservation for entire collision in case of elastic collision? No. Kinetic energy before the collision is equal to kinetic energy after the collision. So now what we are going to do is a question. Let's say there are two blocks of mass 4 kg, 2 kg moving with velocity of 4 meter per second, 2 meter per second. And let's say the coefficient of restitution for this particular reaction is for this particular collision is 0.5. You need to find what is the velocity of both the blocks after the collision. So let's say the 4 kg block moves with a velocity u after collision and the 2 kg block moves with a velocity v after the collision. This surface is frictionless. There is no external force acting on the two blocks. This means that the momentum of these two blocks before the collision will be same as the momentum of these two blocks after the collision. Now first writing the equation of momentum conservation. First writing the equation of momentum conservation. From the equation of momentum conservation, I can write momentum before the collision. Momentum is a vector quantity. To write the momentum, since both of them have got velocity towards right, I am assuming the direction towards right as positive. So I will say the momentum of this first block is 4 into 4, 16. Momentum of the second block is 2 into 2, 4. So the initial momentum of system is a momentum of 20 towards right. Equate this momentum to the final momentum. Finally, I have assumed that the speed of 4 kg block is u and the speed of 2 kg block is v. So the final momentum of system can be written as 4u plus 2v. So you can write 20 equals to 4u plus 2v. Dividing each term by 2, you get 10 equals to 2u plus v. This is your first equation. This first equation came from momentum conservation. Now we can write the second equation. The second equation is the equation of coefficient of restitution. We know that coefficient of restitution equals to velocity of separation upon velocity of approach. Definitely the bodies separate after the collision. But how to write the velocity of separation? Should I write v minus u? Should I write v plus u? Should I write u minus v? Students are always confused. So beta, understand, it's called velocity of separation. The rate at which the separation increase after the collision. Now look at this velocity v. After collision, this velocity v is trying to increase the separation, decrease the separation. This velocity v of the block of mass 2 kg is trying to move them away. This velocity u of the block of mass 4 kg is trying to decrease the separation between them. So what is the velocity of separation? Velocity of separation is the rate at which the separation between the bodies increase after the collision. This velocity is trying to increase the separation. This velocity is trying to decrease the separation. So the velocity of separation has to be equal to V minus U. Sir, how do you know V minus U or V plus U? Beta, again saying, this velocity is trying to increase the separation. This velocity is trying to decrease the separation. So the overall rate of separation will be V minus U. Think that if this second block of mass 4 kg will have velocity towards left U, then how I will write separation, velocity of separation. I will say this velocity V is trying to increase the separation. This velocity U is trying to increase the separation. Both contribute to increase of separation. Then I will write the velocity of separation as V plus U. But in this question, while writing the first equation, momentum equation, since I have taken the speed towards right, that's why keeping it that way and writing the velocity of separation as V minus U. So coefficient of restitution equals to velocity of separation upon the velocity of approach. Now how to write the velocity of approach? Understand that the velocity of 4 kg is trying to reduce the separation, while the velocity of 2 kg is trying to increase the separation. What is the velocity of approach? So this velocity of 4 meter per second, try to make them approach. This velocity of 2 meter per second is trying to make them separate. So the velocity of approach will be written as 4 minus 2. From this second equation, you can get V minus U by 2 equals to 0.5, or you can write V minus U equals to 1. Now beta, this is quite easy to solve. Either multiply the second equation with 2 and add 2u will get cancelled, or simply multiply the second equation with minus 1 and add v and v will get cancelled. Then you can solve for u and v. So kids, now two questions. First question. There is a block of mass m going with a speed v colliding with another block of mass 2m initially at rest. The coefficient of restitution is 1. So this is an example of elastic collision. Remember that in elastic collision there is no energy loss. Energy is conserved, kinetic energy is not conserved. Energy is conserved, momentum is conserved, kinetic energy is not conserved during the collision. It converts from kinetic to potential and then again potential to kinetic. So now here there is a block of mass m moving with a velocity v colliding with another block of mass 2m. Question is, find the maximum elastic potential energy during the collision. The elastic potential energy stored in this system will be maximum at the time of maximum deformation. The more will be the deformation in a spring, the more will be the energy stored about it. So how to find that maximum elastic potential energy stored during the collision? I said in the very beginning, at the time of maximum deformation, both the blocks move with a common velocity along the line of impact. They have maximum deformation at such condition. So now here, at the time of maximum deformation, when both the blocks will be most deformed, okay, I am trying to not show them as block because you should understand that during collision their shape will change. Okay, so at the time of maximum deformation, let's say they move with a common velocity u. How to find this common velocity u? You can do momentum conservation. You can say initial momentum of system mv. I will write solution here. Okay, mv equals to the overall mass of system 3m into u. So the common velocity with which the system move at the time of maximum deformation, that will be equal to v by 3. Now they have asked me what is the maximum potential energy. Understand that in case of elastic collision, energy is conserved. Kinetic energy is not conserved. Kinetic energy first converts into potential and then that potential again converts into kinetic. It is not at all that at the time of maximum potential energy, kinetic energy is 0. No, because even at the time of maximum potential energy, the system has got some speed. So the kinetic energy is not 0. There is not 100% conversion. Take it like to understand. Initially you have some kinetic energy of 100 joule. They collide. Out of this 100 joule, let's say 40 joule gets converted into potential energy till the time of maximum deformation, and that 40 joules again get converted into kinetic energy. Okay, so initially you have got 100 joule of kinetic energy, then at time of maximum deformation you have got 40 joule of potential, 60 joule of kinetic, then again after collision you have got entire 100 joule of kinetic. So now here, how to find the maximum potential energy? Find the kinetic energy at the time of maximum deformation, find the initial kinetic energy, subtract them. Their subtraction will give you how much kinetic energy has been lost. The loss in kinetic energy will be equal to gain in potential energy because the energy is conserved. So you will say the initial kinetic energy half mv square, the kinetic energy at this instant half into 3m into common speed v by 3 whole square, and the difference in them, gives you the loss of kinetic energy. That will be the potential energy at the time of maximum deformation. So next question, there are two blocks, one of mass 6, one moving with speed of 6 meter per second, second moving with speed of 4 meter per second. The coefficient of restitution is 0.5. They are placed on frictionless surface, so there is no external force acting. Now question is, find the separation between the blocks 5 seconds after the collision. Find the separation between the blocks 5 seconds after the collision. Now when I ask this question in class, students are like, maybe he has forgotten to give the mass. I have purposefully not given the mass because it is of no use in this question. You know that coefficient of restitution equals to velocity of separation upon velocity of approach. If this is the picture before the collision, I will say that velocity of approach is 2 meter per second. Why? This velocity of 6 meter per second is trying to make them approach each other. This velocity of 4 meter per second is trying to separate them. So what will be the overall velocity of approach? 6 minus 4. So you will write the velocity of approach as 2. So you can say that velocity of separation has to be 0.5 into 2, that is 1. It means that after the collision, the separation between them increases by 1 meter every second. If the separation increases by 1 meter every second, what will be the separation between them after 5 seconds? So after 5 seconds, the separation has to be 5 meters. So two more problem, kids. The first problem, there is a horizontal surface. In a gravity-free region, a ball comes and strikes this surface at some angle theta with the horizontal with a speed v. The coefficient of restitution for this particular collision is E, and they have asked, after collision with this surface, what will be the horizontal velocity, what will be the vertical velocity, and at what angle with the horizontal the ball will bounce back after the collision. One more thing that they have given is this surface is frictionless. So now how to solve this question? You have to visualize two incidences. First, the ball just before the collision and the ball just after the collision. Just before the collision, think the ball is here. The ball will have two velocity, one horizontal component. Since it is gravity free, it won't move on curved path, it will move on straight path. The horizontal component v cos theta, the vertical component v sin theta. Okay, vertical component v sin theta, horizontal component v cos theta. And let's say, kids, just after collision, it has got some horizontal velocity x and some vertical velocity y. Now how to find this x and y? Visualize this. This is the horizontal surface. This is the spherical ball coming and colliding. At the moment of collision, where is the line of impact? Along which line the forces will act? So at the time of collision, the forces will act along this vertical line. Since the ground applies the force on this ball in vertical direction, during the time of collision, no horizontal force acts on the ball. Since no horizontal force acts on the ball, you can say that the horizontal momentum of the ball won't change. So the horizontal momentum of ball just after collision has to be same as the horizontal momentum of ball just before collision. Why? Because during collision, the forces act in vertical direction. This is the common normal. There is no force in horizontal direction. So you can say just after collision, horizontal momentum, let's say the mass of ball is m. Just after collision, horizontal momentum is mx. Just before collision, horizontal momentum is mv cos theta. They both have to be equal. So you can simply say the horizontal velocity after collision is same as original, which is v cos theta. It do not change. Well begun, half done. Now all we have to find is vertical velocity. How to find it? To find the vertical velocity, I will use the coefficient of restitution equation. Coefficient of restitution equation says that E equals to velocity of separation upon velocity of approach. Velocity of separation and velocity of approach should be taken along the line of impact. In this case, the line of impact is vertical. So the velocity of separation will be y and the velocity of approach will be v sin theta. So coefficient of restitution can be written as velocity of separation upon velocity of approach. So you can write the vertical velocity after collision equals to ev sin theta. ev sin theta. What I tell students to visualize from here, let's say there is a horizontal surface, okay, and just before collision, a ball has got horizontal velocity 4, vertical velocity 8. Horizontal velocity 4, vertical velocity 8. And let's say the coefficient of restitution is 0.5. So after collision, the horizontal velocity will be same because there is no force in this direction during collision. But the vertical velocity will be E times the velocity of approach. Velocity of approach is 8. E is 0.5. So the vertical velocity has to be E times velocity of approach, that is 4. So this ball will go with a net velocity of 4 root 2 just after collision at an angle of 45 degrees. So now here, the velocity in y direction came out to be EV sin theta. X direction comes out to be V cos theta. At what angle it will go after collision? Let's call that angle phi. You can say that tan phi equals to y by x, the vertical velocity upon the horizontal velocity. You can write y as EV sin theta and x as V cos theta. So you can cancel out V and V and say that tan phi equals to E tan theta. So now moving on to next example. There is an incline of inclination theta. The surface is frictionless. From some point above this incline, you release a ball. The ball comes, strikes with the incline, and after collision moves horizontally. Question is, what is the coefficient of restitution? They haven't given me mass of ball, not required. They haven't given me at what height it has been released, not required. Nothing is required. Yes. So question is, you release the ball from some height above the incline, the ball falls and after collision moves horizontally. What is the coefficient of restitution? So as to find it, again visualize an instant just before the collision and an instant just after the collision. Beta, for an instant just before the collision, let's say the ball has a downward velocity v, and for the instant just after collision, you can say, let's say the ball has got a horizontal velocity u. For this particular collision, where will be the line of impact? This is the surface, this is the ball. Where will be the line of impact? Along the normal. Now, if this angle is theta, this angle with the horizontal will also be theta. So this angle will be 90 minus theta, and hence this angle between the horizontal and vertical comes out to be theta. One more thing, if this is theta, this is also theta, and this angle will be 90 minus theta. Sir, why are you breaking down so much? Once we'll tell. During collision, the force acts along the normal. This means that no force acts along the plane of the incline. This means that the velocity along the plane of incline just after collision has to be same as the velocity along the plane of incline just before collision. So you can say V sin theta equals to U cos phi. Sir, what have you done? I have done the momentum conservation. Perpendicular to the normal or along the surface of incline, because in this direction no force acts. So V sin theta equals to U cos theta. V, this angle is theta. V sin theta equals to U cos theta. First equation. Second equation. The equation of coefficient of restitution. Coefficient of restitution is velocity of separation upon velocity of approach, where velocity of separation and velocity of approach both are taken along the line of impact. Velocity of separation will be written as U cos 90 minus theta, that is U sin theta, and velocity of approach can be written as V cos theta. Before collision, velocity is vertically downward V. Its component along the normal will be V cos theta. So velocity of separation upon velocity of approach. Now kids, from here, from the first equation, you can say that U by V equals to tan theta. So coefficient of restitution can be written as U by V, which is tan theta, into sin theta by cos theta, which is again tan theta. So you get tan theta U by V into tan theta because of the sin theta by cos theta. So the coefficient of restitution comes out to be tan square theta. So in this next question, we will discuss about many parts, and this is the most frequently asked out question from collision. There is a ball. It is released from some height h above a flat surface where the coefficient of restitution is E. They might ask, to what height will the ball bounce back? How much time it takes for the ball to come to rest? What is the total distance traveled by the ball before it comes to rest? And all these type of questions gets asked. So let's start answering them one by one. First of all, when the ball falls just before hitting the surface, it will have a downward speed v equals to under root of 2gh. Let's say after collision, this ball tries to go back up with a speed u. You will say that coefficient of restitution equals to velocity of separation upon velocity of approach. So here you get that the velocity with which it bounces back after collision is e times under root of 2gh. with this much velocity, to what height will the ball go? When the ball is projected with a speed u up, it goes up to a height which is equals to u square by 2g. So here the maximum height attained will be u square by 2g. That will be equal to e square into 2gh by 2g. So e square into 2gh by 2g, and you get e square h. So this ball, after the first collision, will go up. If it striked here with a speed v, will go up with a speed ev and will go back up to a height e square h. Then it will fall back again through the height e square h, and by the same logic, next time the ball will go up to a height e raised to the power of 4h. I am drawing it separately, but understand that it will keep on bouncing on the same line because there is no horizontal force. It won't keep on going forward. It will keep on bouncing on the same height. So first falls through h, goes to e square h, then goes to e square h, then go e raised to the power of 4h, then comes back down through e raised to the power of 4h, then goes back up to e raised to the power of 6h, and so on. They can ask you multiple questions here. The first question, what is the total distance traveled by the ball before coming to rest? So first thing, total distance traveled. Total distance traveled. So the total distance traveled by this ball will be equals to h, the distance it falls, plus e square h, the distance it goes back up, plus e square h, the distance it again falls, plus e raised to the power of 4h, the distance it goes back up, then e raised to the power of 4h, and so on, kids. You can again write this thing as h plus 2e square h plus 2 e raised to the power of 4h plus 2 e raised to the power of 6h, and so on. If you remove this first part h, then you can say from here forward it is a geometric progression. If I multiply this term with e square, I get the next term. Then I multiply this term with e square, I get the next term, and so on. And you should remember the sum of a geometric progression, a plus ar square and so on comes out to be a upon 1 minus r, given that r is less than 1. So now here the sum of this can be found out. Keep the first term blind. From here you can think of a GP with the first term being 2e square h. So a being 2e square h upon 1 minus r, and the common ratio is e square. So when you take the common denominator as 1 minus e square, you get h minus e square h plus 2e square h. So here you get h minus e square h plus 2e square h. So that becomes h times 1 plus e square upon 1 minus e square. This is the total distance traveled by the ball before coming to rest. They might ask, what is the total displacement of the ball before coming to rest? Displacement finding it easy. Eventually the ball will come to rest on ground, and then the total displacement will be h down. Sometimes they ask, what is the total time taken for this ball to come to rest? Remember that the ball will make infinite collisions with the ground before coming to rest, but it won't take it infinite time. This is called Zeno's paradox, a process which is completing in infinite number of steps might not take infinite time to get completed. So now here, what will be the total time taken? You know that for falling through a height h, the time taken is under root of 2h by g. So for total time, the time taken to fall this first time will be under root of 2h by g. Then since it goes back up to a height e square h, the time taken to go up, since the height becomes e square, the time taken to go up will be e times under root of h, no? Time proportional to root h. So if in place of height you get e square h, then the time becomes e times. So the time taken to go back up is e times under root of 2h by g. Then the time taken to come back down is e times under root of 2h by g. Then the time taken to go back up is e square under root of 2h by g. And then the time taken to come back down e square under root of 2h by g. And this process keep on happening. So how to find the sum of this series? You can think of time as under root of 2h by g plus 2e times under root of 2h by g plus 2e square times under root of 2h by g and so on. If I forget the first term, then from here onward I can see a GP of common ratio E. Beta, why I am not including the first term? Because first term contains an x, do not contain a 2. If the first term would have contained a 2, then I would have taken the whole as a GP. So how to find sum? In the same way, keep apart the first term under root of 2h by g, and for taking this term as the first term and write the sum of this GP, you get 2e under root of 2h by g upon 1 minus e. Finding this sum, you can find out the overall time taken by the ball to come to rest. One more thing, just remember that when you release a ball from a height h, after falling on ground, it bounces back to a height e square h. So if let's say for one particular case, coefficient of restitution is 0.5. So when you release the ball from height h, coefficient of restitution 0.5 means half. So when you release the ball from height h, it will go collide with the ground and bounce back to a height h by 4. Many a time they ask, if the coefficient of restitution is 0.5, what is the energy loss during the collision? Understand, after first collision, the ball comes back to only 1/4 the height. If the ball comes back, for this case, when the coefficient of restitution is half, if released from height h and ball comes back only to 1/4 the height, it retains only 1/4 of the energy in collision. So what will be the loss of energy? 3/4 is lost during the collision and 1/4 is retained. Sir, what if they give me coefficient of restitution, let's say as 1 by root 2? If they give the coefficient of restitution as 1 by root 2, this means that when released from height h, the ball will come back to a height h by 2 after the collision. It comes back up to a height h by 2. This means that the final potential energy is half of the initial potential energy, half the height, half the potential energy. This means that the energy retained is half. If the energy retained is half, half is lost, half is retained. So these type of questions also come in examination. So now we will discuss two important cases that you must remember. The first one, when two equal masses collide elastically. Elastically means the coefficient of restitution is 1, there is no energy loss, there is no momentum loss. The kinetic energy before the collision is same as the kinetic energy after the collision. So now here, when two equal masses collide elastically, they exchange their velocity along the line of impact. Focus on keywords, beta. Exchange their velocity along the line of impact. It means that if we have got these two blocks A and B, and before collision, A moves with a velocity v towards right, I can be 100% sure B will have the same velocity as that of A after the collision. So same magnitude, same direction. Similarly, what will be the velocity of A after collision? Say they exchange their velocity. So the velocity of A after collision will be exactly same as that of velocity of B before the collision. So U towards left. So two equal masses colliding elastically exchange their velocity along the line of impact. Important thing. Okay. The next important case, when a very heavy mass collides with a very light mass. So let's say there is a small insect going and colliding with a truck. So if one of the mass is very, very heavy compared to another mass, then do not apply the equation of momentum conservation. That will be a waste of time. When one very light mass collides with one very heavy mass, you can assume that there is no appreciable change in the velocity of heavy mass. No matter with what velocity a mosquito flies and collides with a truck, the velocity of truck won't change appreciably. So now here, the basic concept that you have to remember when a very light mass collides with a very heavy mass is that there is no appreciable change in the velocity of heavy mass. So the velocity of heavy mass after the collision is near about same as that of before the collision. So now here question is, what is the velocity of both the blocks after the collision? So in these type of question, beta, don't do momentum conservation. Just think this way. Since this mass capital M is way heavier than the small m, definitely when the collision takes place, this small mass applies some force on the capital mass, heavier mass. Since this heavier mass has got a velocity of 6 meters per second towards left before the collision, after the collision that velocity should be little bit less than 6. but we take it like 6. So what is the velocity of much heavier mass after the collision? Same as before the collision. Now what is the velocity of this smaller mass? How to find it? They have given us that the coefficient of restitution for this particular collision is 0.4. Then how to find the velocity of lighter mass? Let's say the lighter mass goes with a velocity v. We can write here the equation of coefficient of restitution. The coefficient of restitution 0.4 equals to velocity of separation upon velocity of approach. The velocity of separation, the small m is trying to increase the separation with speed v. The capital M is trying to decrease the separation with speed 6. So the velocity of separation should be written as v minus 6 upon velocity of approach. Velocity of approach, before collision both are moving towards each other. So both the velocities are trying to make them approach. So you will write the velocity of approach as 6 plus 4, that is 10. So on cross multiplying, here you get 0.4 into 10, that becomes 4, and this 6 comes here. So the speed of this block after the collision is 10 meters per second. In these type of question, don't make the equation of momentum conservation. Remember that if one mass is way heavier than the other mass, then the velocity of heavier mass remains nearly the same even after the collision. So the last example in collision. Beta, this particular example is explained in one page in NCERT, so that makes it very important. So listen carefully, it's a very easy thing, but listen carefully. If there are many ifs in this particular example, if there are two masses with one of the mass initially at rest and the coefficient of restitution for collision being 1 and the collision is oblique, it is not head-on collision, they strike at some angle. So if there are multiple ifs here, two bodies of equal masses, first if, second, with one of them initially at rest, second if, they collide elastically, third if, and the fourth if, that they should collide obliquely. Obliquely, same mass, coefficient of restitution 1 and one of them at rest. If these four ifs are maintained, then a special condition takes place. This special condition is that if one of them is at rest and another one comes and hits obliquely just before collision, both have same masses beta. This has got velocity v. The second one is at rest. Just before collision, let's say they hit here and this is their common normal. So this is the line of impact. You can break down the velocity of this first sphere into two components. One, along the line of impact v cos theta. Second, perpendicular to the line of impact v sin theta. This is the picture just before collision. What will happen just after collision? In the last slide, I said that if two bodies of equal mass collide elastically, then they exchange their velocity along the line of impact. Here we have got two bodies of equal mass colliding elastically. So they should exchange their velocity along the line of impact. So what will be the velocity of first body along the line of impact after collision? What has to be the velocity of second body along the line of impact after the collision? Since just before collision, this second body has got no velocity along the line of impact and the first one has got velocity v cos theta, exchange their velocity along the line of impact. This means that just after collision, this first sphere will have zero velocity along the line of impact because that was the velocity of second body just before the collision, and it will still maintain this velocity v sin theta, while the second one will get the velocity of first one along the line of impact. So that will get the velocity v cos theta. The important condition that happens here is both the bodies move perpendicular to each other after the collision. Why? If there are so many ifs, this question is important. If you play the game of billiard or pool or snooker, you shoot one ball towards the other. When one ball goes and collides with the other, they are marble balls. Coefficient of restitution is nearly 1, not exactly 1, nearly 1. Second thing beta, both have equal masses. One of them is at rest and the white ball goes and hits it. If you ever have played pool, in such a case, two ball moves perpendicular to each other after the collision. So if the four ifs are maintained, both should have same mass, coefficient of restitution 1, collision should be oblique, and which is the fourth one? rest, coefficient of restitution 1, collision should be oblique and they have same mass, then that both bodies move perpendicular to each other after the collision. Next time I will see you guys with rotational. Till then, keep working hard, keep learning. Bye bye.